Alright, hello everyone, I'm Kydo, I'm from Eigenlayer, I'm a critical researcher. Today I'm going to talk about Kydo invented Eigenlayer. Just a quick disclaimer, I'm a very fake researcher compared to everyone sitting here, and I didn't get the memo. Today's title is research talk, and so mine is going to be pretty engineering focused and design one is, disclaimer ahead. So I'm a very fake researcher. Okay. First thing is the way you're going to reference, this article or this slide is going to be you could have invented Eigenlayer, YCIE, YC, YC, YC. So you're just going to call it the YC piece. I said I'm a fake researcher, and the reason why it's going to be called the YC piece is I really hope once you understand what Eigenlayer is on the technical level and implementation level, you can brainstorm about new and brand new ideas. All right. So. First, the quiz. What is Eigenlayer? Do you think it's A? Who's familiar with A? Alright, perfect. Who's familiar with B? Oh, we have two. Oh, very happy. Alright, so at the end, you're gonna see B and you're gonna I understand it now. It's Eigenlayer, and I can explain from first principle why is it designed this way. So the goal is we're gonna go through 4 steps. Alright, the first step is understand what is a problem. The second step is, okay, this is a problem. What are requirements we need to do to solve that problem? The third one is, let's build an MVP given these requirements. Lastly, let's build a product on this MVP, right? Very, very clear and straightforward flow. Hopefully we can have time to finish everything. First is a problem statement. The problem statement can be summarized in this. Bootstrapping any decentralized infrastructure is difficult. Why is it? Oh my god, I don't want to write what to left and right so much. Why is it difficult? Because crypto aims to remove intermediaries, and when not possible, that we have to be able to decentralize it in a way to increase the security and resilience. Sometimes decentralization may not be the only way. Using a trusted execution environment and other techniques are also viable. So why is building a decentralized service is hard? The first thing is decentralized services always need consensus, and I swear to God, okay, and consensus is hard. There's a lot of people here. I don't want to block it with you. Okay. Consensus mechanism is hard. You have proof of authority, which is very similar to a multi-sig. It's very centralized. No, I'm just kidding. We can move it to here a little bit more. Yeah. You're good. Oh my god, this is perfect. It's pretty centralized. The other way that people normally reach consensus about many different nodes is proof of work, but it's very wasteful energy, has its good benefits. I'm not going to go into that. Lastly is where most people nowadays use to coordinate a large set of nodes is proof of stake. And the stake in the proof of stake part is the actual difficult part. And why is that? Because most of the time, stakes represent some kind of economic, financial value. So basically, you have a network, you want someone to provide capital to contribute to security, right? So it's very difficult between the people who are developing these systems, who are generally engineers, really technical folks, connect them to the capital allocators, the stakers. The second is, whenever in the current proof of stake scheme is whenever you want to contribute security to any system, you essentially have to buy their token. Their native token are generally very volatile. They have much higher inventory risk, meaning when you hold it, you have to be very, very well compensated for it. The last part is because you're holding a native token that's not ETH, which is already generating the risk-free 4%, 5% yield. You have to always add additional yield on top of your proof of stake network. So you just print more tokens to ensure people can get on your network. The last part I'm going to touch a little bit deeper is just basically where you have different middlewares trying to bootstrap different proof of stakes network using their own tokens. You fragment security, which is leads to the current day and age where other than bridges, no protocol really integrate with any other third level protocols. So just talk about a little bit each of these a little bit more in depth. The first one, it's difficult to identify where the stakers are, and there's no single place where developers can find stakers. And the key thing behind this is you think of the current way how any system, look at Cosmos is a great example, how any system bootstrap their security is they raise a large ground from VCs. And these VCs then in turn become validators. And because they have their capital holding requirement, they get their lock anyway, et cetera, et cetera. And these VCs basically become the anchoring thing. But it's very limiting, right? Because that means only these people who have larger money can contribute capital and earn a big chunk. So that there could be another way for stakers to interact with the infrastructure developers. The second and third are very much similar, which is whatever for a new protocol to exist, you want people to buy your token, whether it's Atom, Osmosis, or Neuro Cosmos chain, you want them to hold a token that can very likely go to zero. So in order to compensate for that risk or reward for that risk, you give them very, very high reward rates. So it's very common for 20%, 30%, even 50% APRs in Cosmos world for encouraging people to hold your native token. And that just basically is very bad because you have this death spiral where you have to print more tokens, so people sell your token price goes down, so you need to print more and more of your token, and the negative feedback is very, very bad. And the third part is, on top of this, you are also competing with other opportunity costs, right? If I just buy ETH and I stake it, I earn 4%. So if I buy your native token, then I should really, really get much higher than 4% plus whatever the inventory risk I feel like. And the last part is, this fragmented security model. So this is, I think, the device diagram to illustrate this. Let's say a dApp is living on Ethereum and needs 3 ADSs. Here, ADS just stand. You can think of it as middleware, like a bridge, an oracle, and things like that. And on each of these middleware ADS, they have a ability of economic security budget for them to be attacked. So now you see, even though you live on Ethereum, whenever you rely on these different services to attack your protocol, is the lowest denominator, right? What if there's another way where these 3 ADSs, instead of having their native token, they all become ETH, right? And you have 13 billion at the base layer. They all share security among each other. The dApp, the cost to corrupt the dApp now, changed from 1 billion to 13 billion. I don't think you can see the bottom, but you get the point. So these are the 4 basic problems. And now we're just going to go through them and see, how we're going to solve them. The first one is there's no platform to connect them. Second, they have to hold the native token. Third is, you're competing with opportunity costs. Lastly is fragmented security. We're going to take a quick pause, see if there's any questions. All right, perfect. So if we want to build this Eigenlayer protocol that we want to solve these different problems, we need to first become a platform. I'll explain what that actually means. I think it's pretty obscure at this point. Second, you should be able to offer economic security using any tokens, right? You should just be able to use it for the native token, so that you don't need to run into this inventory risk problem. The second one is it will be better, or potentially could be interesting if you are allowed to lower the opportunity cost by earning different things at the same time. Lastly is through some sort of mechanism we're calling it restaking, you should be able to achieve full security instead of fragmentation of the security we demonstrated before. So we're going to build out. Right? We have the 4 things. We're going to build each one out. The first one is we need a platform connecting stakers and infrastructure developers. And what does that even mean? So we're going to run through a very simple diagram of what is a current proof of stake protocol. So you have stakers who stakes into the protocol. You have some developers who are writing the protocol software. And at the end, the protocol serves some kind of user. Let's say, for example, that I use Oracle as an example. The end user may be some smart contract on Ethereum. So the promise that the protocol, this Oracle, provides to this Ethereum contract is whenever you query a price feed, I'm going to return a price feed to you, given some economic security prediction, given some different assumptions have been made. Does that just make sense, right? This abstraction. Perfect. So now is what happens when this promise is broken, right? When the protocol promises its user something but doesn't deliver at the end. So when the promise is violated, we're gonna basically someone in the protocol, basically the stakers, and here the stakers are the validators, they're the same thing for now. Bear with me. They're gonna be slashed, right? Because that means someone was malicious, some guarantee was broken, therefore they're gonna be slashed. So this is actually the entire abstraction, if we go high enough, of any proof of stake system, which is developer writes codes, staker contribute capital into a protocol. Protocol delivers a promise to the user. If the protocols didn't fulfill that promise, the stakers get slashed. Developers design commitments. The protocol stakers make these commitments by staking into the protocol, and the protocol enforces these commitments. All right. So how do you actually build this platform, right? This is the abstraction of proof of stake is, right? Connecting between these two parties. You actually just need two things, right? You need the ability to make commitments, and you need the ability to enforce commitments. How do you make a commitment? You can write some code. How do you enforce a commitment? By running some function. Where? You can do it on Ethereum. You can encode your commitment into a smart contract as any protocol, Uniswap, all these things. You can think of it as making commitments. And enforcing a commitment is by calling some function. In concrete term, this is what it would look like. You have some staker that can stake into a pool, and there's some slashing or commitment logic coded into the pool. And if the user or the staker violates this commitment, anyone can call a function and slash the user. So the API will look something like this. I'm going to give you a quick second to read while I take a sip of water. So let's first look at the functions. You can stake into the protocol, very common. Once you stake, I track your amount, I track your balances, and also you can withdraw. And lastly, anyone can call the slash function, pass in some sort of identifier for the staker and some sort of proof. And this proof is purely customizable, right? Because it's whatever logic you put into this token pool. So for example, if you want to bootstrap a very simple proof of stake chain, a blockchain, then you can say, hey, if this staker double signs at the same block, then I'm going to slash it. So this proof will be 2 block headers under the same block number. So that's would be one example, and you can come up with any example you want for the slashing condition on any proof of stake system. All right, so we check out one. So that entire thing, just 2 symbols. Check out our first requirement, enabling this platform connecting these 2 parties. The second one is we can offer economic security using any token. And that one is solved because we're on Ethereum. There are a lot of ERC20 tokens we can choose from. The third one, we're going to take it easy and just say we're going to use Steep, or we're going to use Rocket Pool ETH, or we're going to use CBE. Right? So I can provide some ERC20 token as economic security, at the same time being exposed to the underlying Ethereum root workflow. I'm doing some cheats here on the third bullet points because that one alone is going to be a standalone talk on how we actually do native restaking and how we track balances across consensus layer and execution layer. And the last part is restaking. This part we haven't touched on. Basically, how do we solve the fragmentation of security problem, and if we can achieve shared security? So this is a current design, right? You deposit something into the token pool. Token pool has some slashing condition subject to it. And then you go into the same security fragmentation problem, right? If I'm staked this token pool, I can stake into this token pool, which have a different which have a different commitment logic, etc., etc. So one way we achieve this is by compartmentalizing or modularizing the slashing function. So the way we do it is the following. On the token pool part, we remove the slashing function. We have a new function called enroll. The way you can think about enroll is the user would deposit the staker would deposit stake their tokens here, and basically whenever they want to make a commitment into some slashing condition, they will enroll into a slasher contract. And the slasher contract is basically a mapping and also a slash function. The slash function is the same slash function we talked about from the previous part, which basically takes the staker and some proof. If the slash function basically returns a Boolean value, it's true, so it's going to set whatever the staker address is to its slash. Does that make sense? So now if I'm a staker, the flow of depositing is going to be the following. I'm going to call the stake function. I'm going to stake into the token pool. Let's say I want slasher 1 and 2. I'm going to call the enroll function, pass in the slasher contracts, and I'm going to enroll in these. Let's say I'm malicious. Slasher 2, what would happen is anyone can submit a proof to slasher 2, and this mapping of my address would be frozen. On the withdrawal side, whatever staker wants to withdraw, the token pool will just check with individual slasher that the staker is enrolled in and see if the staker is currently being slashed. If it's slashed, then we revert and your withdrawal is incomplete. Any questions?
Question.
Yes.
Like, how do you coordinate the state update between essentially committing to multiple slashable events?
How do I?
So let's say I commit to securing multiple protocols at once.
I secure to multiple and I cheat at the same time.
Yeah.
I'll touch on the question at the end because I think going on that tangent, I think I'm not going to be able to. But that's a great question. Okay, so we check out this requirement, right? By using this design of calling enrolling, we can compartmentalize the slashing function and achieve at the same time post security. But at the same time, Louis' point, which is there's some caveats involved that could be potentially interesting. Okay, and actually we designed Eigenlayer. This is the most minimal viable protocol of what Eigenlayer is. Everything I'm going to talk about from this point on is actually making it into a product. But there's a lot of features here that it's not going to be easy for developers to use, not going to be easy for stakers to use, etc., etc. But this is actually the MVP of Eigenlayer. All right. So how can we make it into an actual product? The first thing we're gonna thing we realize is staker doesn't really always want to be validators, right? They don't want to operate their own thing. What a shocker. So the way we want to do this is we're going to add the role of the operator into Eigenlayer. So basically, if you're a staker, you can provide the tokens, you can delegate your token shares to some operator running the off-chain software for you. I'm not going to go into every single variable here, but you can think of it, we're going to track the staker balances, the operator balances, the staker operator relationship, and then a bunch of other things. But if we do this, right, everything is in a token pool. It's very messy, a lot of different contracts. It's gonna get really overblown, not very modular. The way we designed it is we compartmentalize all the sort of the operator functions into what is called the delegation manager. And delegation manager basically tracks which which staker is delegated to which operator, what's the status of each operator, what ABSs or infrastructures is the operator enrolled in. So contract is going to be a lot simpler. So the token pool is going to be tailored towards the stake. You can stake and you can withdraw. The delegation manager is going to be tailored to the operators. Anyone can call the delegate to delegate to any operator. The operators can enroll into any slasher and also exit. The slasher stays the same way, which is basically keep a run mapping. The only difference here is this address variable will no longer track the staker, but only track the operator. This is right, the operator is the one who's running these different things. The second thing we identify is this design only supports one token at a time, right? So if we wanna do this thing for Steve, we have to design all this contract. Now we want to do it for Rocket Fleet, we need to replicate all these contracts. Right? It's very, very cumbersome. So is there a way for us to support more than one token at a time? Very simple, we're going to use the Uniswap liquidity pool model where you have a token manager that tracks all the corresponding token shares everyone have in the individual token pool. And you can think of an individual token pool just holds one kind of token. So this would be Steve, this would be Rocket Fleet, this would be CBE, etc., etc. We're not going to go over this, but it's a simple LP accounting model for keeping track of pool as well. This part is a little bit more tricky, which is what I call the expanding ABS design, because in the current design there's actually a very critical flaw. So this is one attack vector that's very in the current design that could be happening, which is at time 0, the first red arrow, the staker or the operator commits some malicious behavior. Right after that, the staker plus operator withdraws from a Eigenlayer right away. And at some other later time, finally some fraud is detected and people submit the fraud proof to Eigenlayer to slash this specific operator. However, there's nothing to slash at this point because the malicious operator plus slasher has already withdrawn from the protocol. So this is a very classic, unbonding period problem for most proof of stake blockchains, where you want to have at least enough time for anyone to submit the property to the blockchain or to broadcast, so you understand some fraud has been committed. We're not gonna change anything on design, but we're just gonna add one variable that we're gonna check during the withdrawal period. And this variable is basically we're gonna call the unbonding period. It tracks for this lives inside the delegation manager, meaning for each operator, there's going to be an unbonding period. For simplicity, you can think of the unbonding period as some fixed number, like 7 days or 14 days. But more dynamic, it can also be set dynamically based on if I enroll in /1, /2, and /3, I'm going to take the longest unbonding period of the slasher I'm currently enrolled in, since this is a very individual infrastructure specific variable. Token manager. Oh, there's a question?
Doesn't that defeat one of the purposes of Eigenlayer, namely the one that the stakers don't want to lock their stake for too long because of the volatility of the coins?
No, I don't think that was part of the requirement we're trying to hit, right? The requirement, that might be another problem, right? Then you can get around that by building a sort of like a liquid restaking token on top of Eigenlayer. Fun fact, there's actually 11 liquid restaking protocols on top of Eigenlayer. More now? Oh, I'm sorry. There's definitely ways to get around that for the liquidity problem. Because this unbonding period, we're also going to change something on the withdrawal period, right? When the token manager is the only one who can coordinate the withdrawal. So instead of you can withdraw right away, you need to queue your withdrawal and then complete with your withdrawal at a later date. So there might be adding some user complexity, but it's going to be needed to make sure the design is safe and sound. All right, last point, very, very, very simple, is what I call modularizing the slasher. So why is modularizing the slasher needed? If we go through the the workflow of how do we even withdraw from this complex system, right? I talked about withdrawing very simply in the beginning. We're going to walk through it one more time. So this is how you withdraw from the system. The staker would basically tell the token pool, hey, I want to withdraw. The token pool is going to check with the delegation manager to which operator is the staker delegated to, right? After that, we know that which operator is actually running the staker's tokens. We're going to check which is this operator enrolled in, right? It's a which slasher. And then it calls individual slasher 1, slasher 2, and all the slashers the operator is enrolled in to check if the operator is frozen. There's a lot of cross-contract calls, and just in general, cross-contract calls are expensive, especially for a person who staked 500 USDC or 0.5 ETH into the protocol. It would be really cost prohibitive for him to withdraw. So what we're gonna do is we're gonna modularize the slasher even more, such that individual slasher will not track the mapping. Only the slasher manager will track the mapping. So if anyone submits a proof to slash a certain operator, we're going to change the mapping variable inside slasher manager for that specific operator to be true. So now when you're withdrawing, you don't need to call individual slashers anymore. You just need to call slasher manager to know the status of any given operator. And you have invented Eigenlayer. That's the entire end-to-end design from the problem all the way to the protocol it is today. So just a huge caveat. I talk about slashing a lot, slashing manager here and there. A lot of these designs are not ossified yet, so there could be still changes to the final protocol. But this is a great mental model for everyone to have on how this Eigenlayer to work. If you want, please scan this QR code, and it's going to give you a tweet prompt. You can just send that. I would greatly appreciate that. That's in my KPI, so so that would really help me out a lot. Okay.
I'll learn from you for the social media support next time.
Yeah. All right. Any questions before I go here? Josh.
What are the limitations on an operator choosing to do fewer things? Like an operator is opted into certain flashing conditions. If you're an operator and you're oh, there's a bug, or you just want to reduce your thing, but you have however many people delegated. Is an unbonding period for a given staker to pull out of delegating to an operator, right? Can an operator what is the restrictions on an operator's time period of pulling out of a given staking thing?
Yeah, so the question is how long is the unbonding period?
But it's like an unbonding period on like the operator versus like a
Because
delegation
whenever you do
operator.
any change of like delegation, there's always going to be
You just
a
flatten it to like one.
Yeah. But it's very much, we're not sure how that going to be in the actual implementation.
Will the slashing part become some source for MEV? I believe there will be a lot of complication around the slashers, right? We will try to be the first similar to the liquidation for ending thoughtful.
You're saying that there will be,
Yes,
there
yes.
could be, so the question is, could there be MEV when submitting the slasher transaction?
Yeah.
Any transaction has MEV. In my view, I don't think there's going to be a lot because you're not like liquidating some position. You're just like calling and changing a variable. You don't get anything in return. You could, but you don't. Not in this design yet.
So here, for example, if they trigger the slashing, they won't get any reward, or there's a split between the.
Oh, there could be. Then if there's some reward, then you have some external keeper bots who are being flash to submit that. That's perfectly fine. Yeah.
2 quick questions. Can you go back to the last slide? Yeah, I thought it was YC.
It is twice. I'm sorry.
Okay, but no, actual question. Okay, so on the unbundling attack that happened on L1 PBS, there was like this scenario where a validator committed to take an action, but then like also did this other action because the reward was greater than the slashing risk. Are there any like ABS where that could potentially be a thing in Eigenlayer?
Yeah, so the question is, what if the cost, the formal way of for us to think about it is, what if the profit from corruption, meaning deviating from the protocol, is higher than the cost of corruption? Then any rational, right, if you assume everyone's rational, then that will be a problem. Right? The one way you can get around that is, make sure you have a higher capital pool, so you increase the cost of corruption. That's one way. The other way is you just make it cryptographically impossible for anyone to, exploit the protocol from that perspective.
In that case, how to prove that by doing the censorship on the PBS? Generate some proof that the user is doing something wrong.
You have a question?
I have a question, but I'll add to the exit liquidity point about operator design. There is a project that's working on other than just liquid restaking tokens and guys from the payments that are working on like a secondary market for positions of operator positions and staker delegated positions, so you can buy or sell and exit some of those without being part of a liquid restaking token. So again, another ABS that's trying to build something secondary for context.
Can I just call us back to this question on
Yes.
multiple withdrawal or multiple slashing conditions?
Alright, I'm going to test this out. Okay, this is my analogy. I don't think it's my way of understanding this system. So let's say I'm a student and I'm in 5 classes. I make a commitment to all the teachers that, hey, if I cheat on my exam, I am going to... Sure, let's go with that. I'll kill myself, right? And then, on the final exam day, I cheated on all 5 of the exams, right? I cheated on all 5 exams at the same time, right? And I killed myself. Now the question is, did I fulfill my promise? Did I fulfill my commitment? I did, right? But now you replace, cheating on the exam with violating an ABS, and then commitment, and then for killing myself, I'm going to burn some amount of ETH. Right, so I think the way I would explain it is yes, that could be a problem, but it's not going to be a problem because you actually fulfilled your commitment.
But won't it just accumulate the rewards you get for cheating, or like if you cheat all, if you cheat like 100 times, that would be like a lot of.
Yeah, so that's my question. Like, is there no leverage? So if you have 32 state that's slashable, and let's say one slashing event is like 1 ETH burned, you can only commit to 32 slashers.
Yeah, that's good. So I think we're touching a lot on like our future stake short models. In the current one, stake slashing is going to be like a 0 or 1 thing for now. So you get slash, you slash a little bit. The second one is, you think in this model, I don't even talk about the 32 ETH because I didn't even touch native restaking. Right, this is just you depositing some token, right, into the protocol. So basically, for the operator you're enrolled in, let's say this operator has a 100 million ETH. Oh, maybe that's a little bit too much. This is a really great operator. This operator has 500,000 ETH, right? If he committed something wrong, he will be slashed for the full amount, right? It's just basically a frozen status on the slasher manager, and he couldn't do anything. So, but in the future, I think you're explaining is like, oh, what if I don't make this like all or nothing commitment, but I'll make a bunch of smaller commitments to a lot of different people? Then yes, definitely, that's like one protocol we're thinking about is called stake short. Mike, I think this is probably the last question. I want to give Mike some time as well. Yes.
Yeah, I guess my main, and I've given you this feedback before, but my main issue with the term economic security, especially in terms of delegated stake to a node operator, is that like the number 10 billion looks really big, but it's not actually the amount at stake for the node operator themselves. And it's just like the classic principal agent problem. So curious how you guys are thinking about this issue where, like, as a node operator, I'm playing with someone else's money, not my own. You know?
Yeah, that's a good question. There's two ways to think about this question, in my opinion. Oh, this is my opinion alone. The first one is, okay, can we solve principal agent problem? I would say good luck. The second thing I've been thinking about is through the way of how do I lowering the barrier to become an operator. And there's actually an amazing design that recently just posted on our research forum. It's about actually using PBS for operators and how you can delegate the role of running these ABS outside at the same time to solve your problem, such that the outside people who are running these ABSs have enough economic stake, so they have skin in the game to alleviate the principal agent problem. Anyway, I hope that's a good wrap on the talk. Thank you, everyone.